Hi, I'm back with question 5 from the Depth in Physics paper. This is about two-source interference. We've got a sodium lamp, double slits, we get an interference pattern projected onto the screen over here. This is the interference pattern as we look at it, with the points A and B marked as they are on the screen here. So we've got some reference there. The first part of the question is to calculate the wavelength in nanometers of the sodium light based on the measurements that the student has taken. Note that it's in nanometers, so we're using a prefix. You have to take that into account when you're actually writing your answer down here. And the values here, you'll see that they have different uncertainties, and that's going to be important for a subsequent question. Right, let's get started with this. We've got distance between the two slits is 0.8 millimeters. Distance AB, that's that distance there, is 6 millimeters, and the distance from the slits to the screen is 1.6 meters. The first thing to appreciate when we're doing this calculation is we need to know the fringe spacing, x, and we are given this distance AB. That's for 5 fringes. So we've got 1, 2, 3, 4, 5 x's there. Let's work out what x is so that we can then use that in our calculation. So 5x is equal to that distance there, which is 6 millimeters. And that means that x is 6 over 5, which is 1.2 millimeters. That's the first thing. That's worth a mark. Then we're going to use the equation for two-source interference to work out the wavelength directly. That's AX over D. And now we substitute our values in. We need to take into account the fact that we've got values stated in millimeters here, so we need to add in the appropriate prefix conversion. A is 0.8 times 10 to the minus 3. X is 1.2 times 10 to the minus 3. Divided by D, which is 1.6, no conversion. And when you calculate that, it comes out as 6.0 times 10 to the minus 7 meters. But as I said, we need to write that in nanometers. So we've got 2 marks here, correct substitution, correctly worked out x. So now let's convert this into nanometers. If we change the power of 10 here to minus 9, which is what we need. Nano is times 10 to the minus 9. If we change this, that's dividing by 100 here, so to compensate for that we're going to multiply this number by 100. That gives us 600, so that's 600 nanometers. So we write 600 down there, and that's where you get your 3 marks. 1, 2, 3. Okay, on to question B. So we've got question B, which is looking at the actual slits themselves, how they were made. They were made by taking a microscope slide and then covering it in black paint, and some lines were marked in there, some vertical lines, to give us the 2 slits. We now need to describe how you could reduce the uncertainty in calculating the value of the wavelength of the light when carrying out the experiment that we've just looked at. In your answer, include how to achieve the conditions necessary to produce a visible interference pattern on the screen, how you would make the measurements, and identifying the measurement which will give the greatest uncertainty. So really we want to concentrate on here. This is telling us what needs to go into our answer here. So let's start off with the conditions necessary to produce a visible interference pattern. What we need are 2 sources of coherent light. Coherent is the key thing here. So the light from S1 and S2 must be coherent. That's a key point. You've got to appreciate you need coherent light. I will go through the points in a minute to star the ones that are key ones for getting top marks. Again, this is one of those questions where the answers are banded. You've got high, 5 to 6 marks, medium, 3 to 4, low, 1 to 2, and then 0 marks. So I'm tackling this as if we wanted to go for the top marks, which of course we do. How do you get coherent light? So this is a follow-on from that point there. We can place a single slit sorry, that's bad writing there, between lamp and double slit. So what that single slit will do, it will cause the light, it will act as a single source, and it will cause the light to be diffracted over the double slits. So I'm going to include that. This will diffract coherent light. Because it's behaving as a single source, it's giving us a source of coherent light. Diffract coherent light over S1 and S2. So S1 and S2 are what we're referring to as we're referring to the slits by. So that's 2 marks there. This is a 6-mark question, so we've got to make 4 more points. Let's move on. We've described the conditions necessary to produce the interference pattern. Now, how would we make the measurements? What do we need to measure? We need to measure the slit separation, we need to measure the fringe spacing, and the distance between the slits and the screen. So let's start off with S1 and S2, S1 to S2. I would use a travelling microscope. S1, S2 is the terminology that was used in Part 8, so I'm sticking with that. I would use a travelling microscope because I think, practically speaking, that would be easier than using a micrometer, which you could use, but I think it would be more fiddly using a micrometer because you've got to get the measuring rods lined up perfectly with those 2 slits. Whereas with a travelling microscope, you've got a crosshair on the microscope, you can line that up as you look down on the slide and then move it along without having to hold both of these items. So I think that would be better. Next up, we've got the fringe spacing. That's a small measurement. You want to use something like a vernier caliper, I would say. So the fringe spacing. You could put X or 5X, I think that would be fine, because you are actually measuring 5 fringes there. And lastly, we've got the distance from the slits to the screen. Now, in Part A, that said that was 1.6 meters, so we couldn't use something like a micrometer, a vernier caliper, certainly not. It's probably too long to use a ruler, so I'd go with a tape measure here. We've got 5 marks. The last mark is this last point here. Which measurement will give us the greatest uncertainty? And if we look at those measurements, look at the values, you can see that S1, S2 is 0.8 millimeters, and that's only 1 SF. The other 2 are 2 SF. And the absolute uncertainty is going to be 1 significant figure in each of these. So this one is going to give us the largest uncertainty. Because if you take 0.1 here and divide it by this, you're going to get 12.5%. If you take 0.1 here and divide it by that, you're going to get a much smaller number, and the same for this. So this is the one that will give us the largest uncertainty. Let's write that down. I'm going to state how you calculate it here. So the percentage uncertainty for S1, S2 will equal 0.1 over 0.8. 0.1 over 0.8 is exactly the same as calculating 1 divided by 8, and that equals 12.5%. So what were the key points here? You needed to appreciate that you needed coherent light, and then the 3 measurements, those were key points as well. Likewise, this final one here, to make sure that we covered all of the points that were required for this question, we needed to have something that identified where the greatest uncertainty was. So that's part B. Now on to part C. To reduce the uncertainty in wavelength, the students suggest, how about making the slits further apart? So we increase S1, S2, or A, as I will be referring it to. Discuss whether you think this will reduce the uncertainty. Well, the first thing to do is, let's write down the equation that applies here. So lambda equals AX over D. In this situation, the wavelength of light has not been changed, nor has the distance from the slits to the screen. So those are a constant. If this one is increasing, A, which is the slit separation, then in order for the equation to hold true, X must decrease. So this is increased, this must decrease. Now, if A is getting bigger but the absolute uncertainty stays the same, then its percentage uncertainty will decrease. When I say percent A, I mean the percentage uncertainty in A. Because you do the absolute uncertainty divided by A to work out the percentage uncertainty. But the percentage uncertainty in X will increase. So I think that's worth a mark there. We've understood that the uncertainty in A will decrease, but the uncertainty in X will increase because this has got smaller relative to the absolute uncertainty. That's using exactly the same line of reasoning there, the plus or minus X over X, okay? So this is decreased, this has stayed the same, so that will make the percentage uncertainty bigger. However, we weren't measuring X directly. We were measuring A directly, but not X. We actually measured over 5 fringes, didn't we? So we can write that down. But 5X was measured. And that will reduce the effect of the increase in uncertainty. So that effect will be reduced, and that's worth another mark there. You could say here by a factor of 5. It's by a factor of 5 because both A and X had the same absolute uncertainty. They were both measured to the nearest 1/10 of a millimetre. So going on to the third point here, which follows on from this, if you appreciate that, then you can say the reduction in uncertainty in A outweighs the increase in uncertainty in X. So that would be one thing that you could say there. That would be one thing you could say if you weren't happy with that. The other thing you could say is we can increase D, which will then increase X, and it will overcome that increased uncertainty. So that would be an alternative point you can make if you weren't happy with the third point that I've written there. So those are the points for question 5. All that remains now is to do question 6.